The sky does not crack open. No asteroid burns across the horizon. No wall of fire races over the land. At first, the end of the old world feels almost insultingly quiet. Just heat. A thick, wet heat that sits on the planet like a fever no one knows how to break. Imagine standing on Earth around 56 million years ago. The air feels heavier than it should, like every breath has been left too long in a greenhouse. Forests push far toward the poles. Crocodile relatives lurk in places that, today, would make a reptile seriously reconsider its life choices. The Arctic is not the frozen white desert we know now. It is a swampy, strange, almost dreamlike place, with dark water, broad leaves, and animals moving through a world that should not exist on a modern map. And yet, for the creatures living there, this was not some bizarre alternate planet. This was home. The oceans still rolled. Rivers still cut through floodplains. Tiny organisms still drifted through the sea, building delicate shells so small you could miss them entirely. Mammals, still early in their rise after the dinosaurs' fall, moved through forests that were warmer, denser, and in many places more tropical than ours. Life was not gone. Not even close. But something was beginning to shift beneath all of it. Not in the dramatic way we like disasters to behave. There was no single thunderclap moment when every animal looked up and thought, well, that seems bad. Instead, the change seeped into the machinery of the planet. Carbon moved. Heat built. Oceans absorbed what they could. Weather patterns began to bend. And the world, slowly but unmistakably, started becoming a different version of itself. Which is a deeply uncomfortable thing for a planet to do while everyone is still living on it. The strangest part is that we would never have known this ancient fever happened by looking for one giant skeleton, one crater, or one smoking geological gun. The evidence is quieter than that. It is hidden in mud that became rock, in chemical traces locked inside the shells of microscopic sea creatures, in layers of sediment stacked like pages from a diary written by a planet with very dramatic handwriting. Those tiny ocean fossils, barely noticeable compared to a dinosaur skull or a mammoth tusk, became some of the most important witnesses in the case. Because they recorded a signal that should make you pause, a sudden disruption in Earth's carbon system, the kind of chemical fingerprint that says something enormous entered the atmosphere and oceans. Something powerful enough to warm the entire globe. And that is where this story stops being just a strange chapter from deep time and starts feeling a little too familiar. Because yes, Earth has warmed before. That part is true. It has been hotter than it is today. It has had ice-free poles, steamy forests, and oceans that carried warmth into places we now think of as permanently cold. But that fact is not the comforting little escape hatch some people want it to be. In Earth history, it happened before. Does not mean nothing happened. Sometimes it means forests marched across continents, ocean chemistry turned hostile, animals shrank, ecosystems reorganized, and the recovery took longer than entire branches of life could afford to wait. The last time the globe warmed in a major way, the planet survived. Of course it did. Planets are annoyingly good at continuing to be planets. But the living world had to negotiate new terms. Species had to move, adapt, change, or disappear from the places where they once fit perfectly. And that is the real mystery at the heart of this ancient heat wave, not whether Earth could handle it, but what happened to life while Earth was handling it. Somewhere in those rocks is the record of a world pushed out of balance. Somewhere in those microscopic shells is the trace of a carbon pulse that changed the temperature of the air, the chemistry of the sea, and the rules of survival. And the deeper scientists have looked into that record, the more this event has started to look less like a curiosity from the distant past, and more like a warning written in stone. So the question is not simply, when was the last time the globe warmed? The real question is much sharper than that. What did that warming do to the planet's living systems, and why did such tiny fossils become the key witnesses to a fever that gripped the entire Earth? At first, the clues do not look like clues. They look like ordinary layers of ancient seafloor, pale bands of mud and shell and mineral dust pressed into stone by the weight of millions of years. Nothing about them screams catastrophe. There is no broken forest frozen in ash, no crater rim, no graveyard of giant bones stacked one on top of another like nature had a really bad day and forgot to clean up. Instead, the evidence is almost rude in how subtle it is. A thin shift in chemistry. A change in the tiny shells of plankton. A dark line in the sediment. The kind of thing you would walk past 1,000 times unless you knew the planet sometimes hides its worst secrets in very small handwriting. But when scientists began reading those layers closely, the story inside them got weird fast. In rocks from the deep ocean, they found a sharp change in carbon isotopes, a signal that something had dumped a huge amount of lighter carbon into the ocean and atmosphere. And that matters because carbon is not just some background ingredient floating around in the Earth's system. It is more like a master key. Put enough of it in the wrong place at the wrong speed, and it unlocks heat, shifts rainfall, changes ocean chemistry, and sends living things scrambling to keep up. But here is the twist: this was not just one ocean basin acting strange. The same kind of signal began showing up in different parts of the world, like separate witnesses all giving the same uneasy testimony. Deep-sea muds? Coastal sediments? Fossils from land? Chemical traces from organisms that had no idea they were helping future scientists reconstruct a planetary crime scene. And bit by bit, the case started to widen. Whatever happened was not local. It was not a strange regional warm spell. It was not one swamp having a dramatic phase. This was global. The heat touched the poles, the tropics, the oceans, and the land. It bent the world's climate system hard enough that life had to respond. In the Arctic, the idea of cold itself looked different. Instead of ice sheets and polar bears, picture warm wetlands under months of strange seasonal light, with dawns and sunsets stretching in ways that would make the whole place feel slightly unreal. In what is now Wyoming, forests grew in a world where mammals were beginning to diversify into forms that would eventually seem familiar, but were not quite there yet. Tiny early horses, no bigger than a medium-sized dog, moved through warm forests. Primates clung to branches. Crocodile relatives and turtles lived in places where, today, winter would be a very serious customer service complaint. And all of this could make the ancient warming sound almost lush, almost inviting, like Earth just turned up the thermostat and got more tropical. But that is the trap. Warmer is not automatically gentler. A greenhouse world can be green and dangerous at the same time. Heat does not just make palm-like plants grow farther north. It changes the timing of rain. It changes which plants dominate. It changes where animals can travel, breed, and find food. It changes the rules quietly enough that, at first, life may seem to be thriving, even as the floor is moving underneath it. And the ocean was feeling that movement in a way land animals could not see. As carbon poured into the system, seawater absorbed part of it, and that changed the chemistry of the deep. For small marine organisms that built shells, the water itself could become a harder place to live. Imagine trying to build a house while the bricks are dissolving around you. Not exactly ideal. And because those tiny organisms sat near the base of marine food webs, their trouble did not stay tiny. A disturbance at that scale can ripple upward, touching creatures that never knew the original chemical shift had happened. So now the mystery had layers. The planet was warming. The oceans were changing. The signal was global. Life was reacting. But the most unsettling clue was the speed. In geological terms, this warming happened fast. Not fast like a weekend heat wave. Fast like the Earth system was shoved, not gently nudged. And that raises the question scientists had to chase next. What source of carbon could be large enough, and sudden enough, to leave its fingerprints across the entire planet? The first real break in the case comes from a place that looks, honestly, pretty unimpressive at first glance: mud. Not dramatic lava, not shattered bones, not a fossilized animal caught in its final moment with one claw raised like it was posing for a museum gift shop. Just ancient mud, laid down at the bottom of the sea, layer after layer, grain by grain, while the world above went on being warm, wet, and alive. But mud is patient. Give it enough time, bury it deep enough, squeeze it hard enough, and it becomes rock. And in that rock, Earth keeps receipts. Some of the most important receipts from this ancient warming come from tiny shells made by marine microorganisms, especially foraminifera, little single-celled creatures that floated in the water or lived on the seafloor. They were not trying to become evidence. They were just living their tiny ocean lives, building shells from the chemistry around them, dying, sinking, and joining the slow snowfall of biological debris that blankets the deep sea. But because their shells formed from seawater, they captured a chemical snapshot of the ocean at the moment they were alive. Which is very convenient for us, and deeply unfair to them, since they did not consent to becoming climate informants. When scientists measure the carbon locked inside those shells, they can see whether the ocean was carrying more of one kind of carbon than another. Carbon comes in different isotopes, and during this event, the record shows a sharp swing toward lighter carbon. That is the kind of clue that makes geologists sit up straighter, because it suggests a huge pulse of carbon entered the atmosphere and ocean system. Not a little puff. Not a local burp. A pulse big enough to show up across the planet like a fingerprint left on every surface in the room. And the oxygen in those shells tells another part of the story. Oxygen isotopes can help reveal temperature, and during this interval, they point to a world that got dramatically warmer. The deep ocean warmed. Surface waters warmed. The poles warmed. Places that should have been cool became strange and mild. The entire planet seemed to be shifting into a hotter mode, and the shells were recording it one microscopic life at a time. But here is where the evidence becomes even more unsettling. In some deep-sea sediments, the fossils of bottom-dwelling foraminifera suddenly become scarce. Some species disappear from the record. Others take over. The community changes, as though the seafloor itself had become a harder place to survive. That is not just a thermometer reading. That is biology reacting to chemistry. It is one thing to say the ocean got warmer. It is another to see the residents of the deep ocean start vanishing from the pages of the record. And remember, the deep sea is supposed to be stable. Compared with the surface world, it is usually the slow, quiet basement of the planet, cold, dark, and buffered from a lot of the drama happening above. So when the deep sea starts registering distress, that is not a small clue. That is the basement's smoke alarm going off. Then there are the sediments themselves. In some places, the layers from this interval change color and texture in ways that point to a transformed ocean. Carbonate shells that normally accumulate on the seafloor become harder to preserve when the ocean becomes more acidic. So the rock record can show a kind of disappearance, not because organisms never existed, but because the ocean chemistry made their remains less likely to survive. That is a particularly sneaky kind of evidence, because the absence itself becomes a clue. The missing shells are not silence. They are testimony. Together, the carbon signal, the temperature signal, the disrupted microfossils, and the changed sediments begin to outline the shape of the event. Something injected carbon into the Earth's system. The planet warmed. The ocean absorbed part of the shock. And deep-sea life, far from the forests and floodplains, felt the consequences. But a good mystery does not end when the first witness speaks. It gets more complicated. Because once scientists could see the carbon fingerprint, they still had to ask a much harder question. Where did all that carbon come from? And why did it arrive fast enough to shake the deep ocean itself? Picture a plug of ancient seafloor lifted from the deep ocean, a long cylinder of mud and stone, striped in quiet bands, like someone pushed a straw into Earth's memory and pulled out a sample of time. Most of it looks ordinary. Layer after layer of pale sediment, made from the remains of tiny marine organisms that lived, died, sank, and became part of the slow snowfall of the sea. But then, in the middle of that record, the color changes. The texture changes. The chemistry changes. It is not flashy. It does not look like disaster in the way a burned forest or a smashed skeleton looks like disaster. But to scientists reading the rock, this is the moment the planet starts whispering, something happened here. The first clue is carbon. Not carbon in the vague, background way we talk about it today, but carbon as a fingerprint. In those tiny shells, the ratio of carbon isotopes suddenly shifts. The record leans hard toward lighter carbon, the kind often associated with organic carbon sources, methane, or other reservoirs that have been locked away from the active atmosphere and ocean. And that shift is not subtle in geological terms. It is a sharp bend in the line, like the planet's carbon cycle was walking down a hallway and suddenly got shoved through a side door. But here is the important part: the carbon signal does not say, by itself, who opened the door. It only says the door was opened. That is what makes this clue powerful, and also frustrating. It tells us something enormous entered the system, but not yet whether the culprit was volcanic activity, methane release, warming soils, burning organic-rich sediments, or some messy combination of suspects all making each other worse. And because Earth history rarely gives us a neat villain wearing a name tag, the mystery deepens. However, the carbon was not acting alone. A second clue shows up in oxygen isotopes, and this one points toward heat. The shells of those same tiny organisms carry oxygen signatures that can be used like ancient thermometers. And during this interval, those signatures tell us the ocean warmed, including parts of the deep ocean that normally do not swing wildly with surface conditions. That matters because the deep ocean is not supposed to behave like a kiddie pool left in the sun. It is vast, dark, and slow to change. So if the deep ocean warms, that means the entire climate system has been pushed hard enough for the heat to reach into the basement of the planet. Which raises a question: what kind of carbon pulse is strong enough to warm not just the air, not just the surface, but the hidden depths of the sea? And then comes the third clue, the one that turns this from a chemistry story into a survival story. In many deep-sea records, bottom-dwelling foraminifera take a major hit. These were tiny organisms living on or near the seafloor, far away from the bright surface world. They were not glamorous. No one is making action figures of them, which is unfair, because they were apparently excellent at leaving evidence. During this warming event, many of them disappear from the fossil record in a dramatic turnover. Their communities change. Some lineages vanish. Others move in. The seafloor ecosystem, usually one of the steadier corners of the biosphere, suddenly looks disturbed. And that is a clue with emotional weight, because it tells us the warming was not just numbers in a lab. It was a pressure that reached living bodies. It touched organisms that could not simply pack up and stroll north. It changed the conditions of a world that had seemed buffered from chaos. But even that does not close the case, because the seafloor was not the only witness. The rocks themselves show signs that the ocean's chemistry changed in a way that made carbonate harder to preserve. In some layers, the normal rain of shells becomes thinner or altered, as if the ocean began erasing part of its own archive. Imagine a crime scene where the evidence is not only left behind, but partially dissolved by the crime itself. That is the kind of problem scientists are dealing with here. The missing material becomes part of the message. The absence says, the ocean changed enough that even the dead had trouble staying intact. So now the clues line up in a way that is hard to ignore. A carbon fingerprint. A warming signal. A stressed deep ocean. A change in shell preservation. Living communities rearranged under pressure. Each clue answers one part of the mystery, but each answer opens another door. Because if carbon entered the system, warmed the ocean, and pushed deep-sea life into crisis, then the next question is not just where the carbon came from. It is whether Earth's own feedbacks helped turn one disturbance into a planetary fever. By this point, the rocks have given us a trail: carbon entered the system, the oceans warmed, deep-sea life struggled, and the chemistry of seawater changed enough to alter what could even be preserved. But a trail is not the same thing as a culprit. And this is where the case gets messy, because Earth does not usually commit its geological crimes with one clean fingerprint. It tends to use accomplices. The first suspect looks big, fiery, and appropriately suspicious: volcanoes. Around this time, enormous volcanic activity was happening in the North Atlantic region, as Greenland and Europe were beginning to pull apart. Picture the crust stretching and cracking, magma forcing its way upward, lava spreading across the landscape, and heat baking through layers of rock rich in ancient organic material. Volcanoes can release carbon dioxide directly, and when magma intrudes into carbon-rich sediments, it can cook those rocks and release even more greenhouse gases. That makes volcanism a very tempting suspect. It has motive. It has opportunity. It has a long criminal record in Earth history. But then comes the problem. The carbon isotope signal is strongly tilted toward lighter carbon. Volcanic carbon alone may not fully explain the size and shape of that signal. So the investigation turns to another suspect hiding in colder, darker places: methane. Methane can be stored under the seafloor in icy compounds called hydrates, and if the ocean warms enough, some of those hydrates can destabilize, releasing methane into the water and, eventually, into the atmosphere. Methane is carbon-rich, light in its isotope signature, and a powerful greenhouse gas. In other words, it looks very guilty. The scenario is almost cinematic in the worst possible way. Initial warming begins, the ocean heats up, buried methane starts to escape, and then that methane drives even more warming. A climate feedback loop, like the planet stepping on its own accelerator. However, methane has its own complications. It does not stay in the atmosphere forever, and the amount needed to explain everything may be enormous. So scientists have had to ask whether methane alone could really carry the whole story, or whether it was just one accomplice in a larger operation. And then there is the quieter suspect: organic carbon stored in soils, wetlands, and sediments. In a warmer world, carbon that had been locked away can be released through decomposition, erosion, or burning. On land, hotter and wetter conditions in some places could have changed how carbon moved through forests, rivers, and floodplains. Rivers may have carried more organic material into the oceans. Soils may have breathed out more carbon as temperatures rose. This suspect does not enter the room with lava or bubbling methane, but it may have been everywhere, spreading the disturbance through the everyday machinery of the planet. Which is somehow more unsettling. A catastrophe powered not only by spectacular eruptions, but by normal Earth systems pushed into abnormal behavior. And here is the mini twist: scientists may have started by looking for the source of the carbon, as if the event had one main trigger. But the deeper the evidence goes, the more the question changes. The real problem may not be one source. It may be timing, speed, and feedback. A volcanic pulse could warm the world enough to destabilize methane. Methane could amplify warming, which could change rainfall, which could increase erosion and move more carbon into the ocean, which could further stress marine chemistry. Suddenly, the mystery is not a lineup of separate suspects. It is a conspiracy. Each part of the Earth's system nudging another part, until the original cause becomes tangled with the consequences. That is why this event is so difficult, and so important, to understand. Because if the planet's carbon cycle were a simple machine, scientists could point to one broken gear and say, "There, that was the problem." But the carbon cycle is more like a crowded dinner party where every guest is holding a match, a glass of gasoline, or a very poor sense of restraint. Once the first disturbance begins, the reaction can spread. The atmosphere talks to the ocean. The ocean talks to sediments. Sediments talk to life. Life changes how carbon moves. And before long, the warming is no longer just something happening to the Earth system. It is something the Earth system is helping to build. That does not mean every hypothesis is equally likely, or that scientists have no idea what happened. The evidence has narrowed the suspects, and made some combinations more plausible than others. But it does mean the ancient warming was probably not a simple story with one villain and one weapon. It was a chain reaction, and that changes the stakes. Because if a carbon pulse can trigger feedbacks that make the planet warmer, stranger, and harder for life to navigate, then the next question becomes unavoidable. What did all of this do to the creatures trying to survive on land, where the crisis was not written in shells, but in bodies, forests, and migration routes? On land, the crisis does not appear as a neat chemical curve. It appears as a world that starts rearranging itself while animals are still trying to make a living in it. The ocean gave scientists the carbon fingerprint, the warming signal, and the deep-sea distress call. But land gives a different kind of testimony: teeth, bones, leaves, pollen, soils, and the shifting geography of where living things could survive. So start with the obvious clue: the air was warmer. But what does warmer air actually do to a forest? It does not simply turn the whole planet into a postcard from Florida. Warmer air holds more moisture. Rainfall patterns change. Some regions get wetter, some drier, and seasons can start behaving like they were written by a committee that could not agree on the assignment. Plants respond first, because plants are stuck with the weather they get. Fossil leaves and pollen suggest vegetation shifted as climates moved, with warm-adapted forests expanding into places that would later become much cooler. That answers one question: yes, the warming reached land. But it raises a more interesting one. If the plants moved, what happened to the animals whose lives were built around those plants? That brings us to mammals, which were still in the early chapters of their post-dinosaur story. After the asteroid cleared the stage, mammals had begun diversifying into new forms and new roles. By the time this warming hit, some groups were spreading across continents, exploring habitats, and becoming the ancestors of lineages we would recognize much later. But during this interval, the fossil record shows something strange in some mammals. Their bodies got smaller. Not every mammal, not everywhere, and not in a cartoonishly simple way. But in several groups, including early horses and some primates, scientists have found evidence of dwarfing during the warmest part of the event. So now it leads to a question: the planet warmed. Why would that make some mammals shrink? One possible answer is heat. Smaller bodies can release heat more easily than larger ones, which can be an advantage in a hotter world. Another answer is food. If warming changes rainfall, vegetation, and plant quality, then animals may face nutritional stress. Smaller bodies need less energy, and in a world where resources become less predictable, that can matter. So B helps explain A. Body size may have been part of how some animals adjusted to a changed climate. But then B opens its own question: if shrinking was useful, was it a clever evolutionary strategy, or just a sign that ecosystems were under strain? To get closer, scientists look at teeth. Teeth are excellent little informants. They record diet, wear, growth, and sometimes even chemical traces from the environments animals lived in. Fossil teeth from this time can suggest what animals were eating and how their habitats were changing. If plant communities shift, tooth wear and tooth chemistry can help reveal whether herbivores were browsing in different environments or coping with different food. And now C begins to solve B. The animals were not just passively sitting under a warmer sky. They were living inside a food web that was being reorganized from the bottom up. Plants shifted. Mammals adjusted. Body size changed. Migration routes opened and closed. The warming was not just a background condition. It was an editor, revising the script of daily survival. And then, with that in mind, we can return to A with a sharper view. The carbon pulse did not simply raise the temperature. It created a chain that ran from atmosphere to plants to bodies. Carbon altered climate. Climate altered vegetation. Vegetation altered food. Food and heat altered animals. The same disturbance that showed up in deep-sea mud also showed up in the bodies of mammals walking through ancient forests. That is the part that makes the evidence feel so connected. The ocean record and the land record are not separate stories. They are two halves of the same planetary event. In the sea, tiny shells record changing chemistry. On land, tiny horses and other mammals record changing ecological pressure. In the rocks, carbon leaves a fingerprint. In teeth and bones, life leaves a response. But there is still a missing piece. Because seeing animals shrink, move, and adapt tells us that life responded. It does not tell us how close the system came to crossing thresholds that could not be easily uncrossed. Some species may have found new opportunities in the warmth. Others may have been pushed out of the places where they once fit. And that is where the story gets trickier than a simple disaster narrative. This was not a world where everything died. It was a world where many things changed, and change can be both opportunity and danger depending on which side of the shift you are standing on. A warmer Arctic might open corridors for some mammals to spread between continents. But the same warming might stress marine ecosystems, acidify parts of the ocean, and force other organisms into evolutionary dead ends. So the clues now connect across the whole Earth system: carbon, heat, ocean chemistry, vegetation, body size, migration. But one question still hangs in the air like humidity before a storm. When the planet finally began to recover, did life simply return to normal? Or had the warming already pushed the world into a new shape? The obvious way to tell this story would be to make the warming the villain, and leave it there. Carbon entered the system, temperatures rose, oceans changed, life struggled. Case closed, cue the ominous music. But Earth history is almost never that tidy, and this is where the story bends in a direction that is both fascinating and a little uncomfortable. Because this ancient heat wave did not only squeeze life. In some places, for some lineages, it opened doors. That is the twist. The same event that made the deep ocean more hostile and pushed ecosystems under stress may have helped some mammals spread, diversify, and step into new opportunities. Which feels unfair, honestly. You would think a planetary fever would at least have the decency to be bad in a straightforward way. But evolution does not grade events on moral clarity. It works with whatever conditions exist after the rules change. During this interval, the world was warmer and wetter in many places, and high-latitude regions that had once acted like barriers may have become more like corridors. Think of the far north not as a frozen wall, but as a strange green passageway, a route across continents lined with forests, wetlands, and long seasonal light. For animals that could handle those conditions, warming may have opened pathways between North America, Europe, and Asia. The map of the living world was being redrawn, and some mammals were suddenly able to move through places that had been difficult or impossible before. That means the warming was not just an environmental crisis. It was also a massive experiment in biological redistribution. Some creatures were trapped by the changes. Others used them like a bridge. And this is where the fossil record starts to look less like a list of casualties and more like a map of winners, losers, and creatures that were just very lucky with timing. Early primates appear in North America around this broader window of warmth and dispersal. So do early relatives of horses and other mammal groups that would go on to become much more important later. These animals were not modern horses or modern primates, not even close. The early horses were small forest browsers, more dog-sized than rodeo-sized, and the primates were tiny, tree-living creatures moving through warm, dense habitats. But their presence tells us something important. The world was changing in ways that created new routes and new ecological possibilities. And that complicates the emotional shape of the whole event. Because if you are a deep-sea foraminifera trying to live in an ocean whose chemistry is turning against you, this warming looks like disaster. If you are a small mammal crossing a newly hospitable northern corridor, it may look like opportunity. Same planet. Same carbon pulse. Very different experience. That is the kind of thing Earth does all the time, which is frankly rude but scientifically useful. And it forces us to rethink what a world-changing event really means. It does not always mean everything collapses in the same direction. It means the rules change unevenly. One ecosystem loses stability. Another becomes newly connected. One lineage shrinks under heat or nutritional stress. Another expands into a space that did not exist before. So the question is not simply, was this warming good or bad for life? That question is too small. The better question is, who was standing in the right place, with the right body, at the right moment, when the planet changed the game? And now the evidence from Part 6 starts to click into a sharper pattern. Mammals shrinking was not just a weird footnote. It may have been part of a broader survival strategy in a warmer, altered world. Mammals dispersing across continents was not just a happy travel montage with tiny horses. It was the result of climate changing the geography of possibility. Fossil teeth, bones, leaves, and sediments all start pointing toward the same uncomfortable idea: climate does not just threaten life from the outside. It edits evolution from the inside by changing which traits matter. A small body, a flexible diet, the ability to move through forests, the ability to tolerate heat or exploit a new corridor, all of these can suddenly become more valuable when the world warms. And traits that worked beautifully in the old world can become liabilities in the new one. That is the big reversal. The ancient warming was not only a stress test. It was a filter. It sorted life. It punished some organisms, rewarded others, and rearranged the stage on which future evolution would unfold. The deep ocean records the cost. The land record shows the reshuffling. And together, they reveal a planet that did not simply get hotter and then cool back down like nothing happened. It passed through a biological checkpoint. Some lineages made it through changed. Some spread into new worlds. Some disappeared from places they once belonged. And the world after the fever was not just the old world with a lower thermostat. It was a different ecological arrangement, built from survivors, opportunists, refugees, and the unlucky dead. But that leaves one more piece of the mystery still unresolved. If warming can both damage ecosystems and open new evolutionary doors, then how do we judge what recovery really means? Is it the return of a stable climate, the rebuilding of ecosystems, or simply the moment when the planet stops changing faster than life can keep up? By now, the investigation has stopped looking like a single line of evidence and started looking like a web. The deep ocean says the chemistry changed. The carbon isotopes say a huge pulse entered the system. The oxygen isotopes say the world warmed, even down into the darker, slower parts of the sea. The sediments say the ocean became more difficult for carbonate shells to survive in the record. The fossils say some deep-sea communities were hit hard. And on land, leaves, teeth, bones, and migration patterns say the warming did not stay politely offshore. It climbed into forests, shifted habitats, changed food webs, and helped redraw the routes animals could take across the planet. At this point, the clues are no longer whispering. They are starting to talk over one another. And what they are saying is that this was not just a warm interval. It was a system-wide disruption. Think of Earth like a house where every room is connected by vents, pipes, wires, and hidden crawl spaces. You cannot flood the basement and expect the living room to stay perfectly normal. You cannot fill the kitchen with smoke and assume the bedrooms will never smell it. During this event, carbon entered the atmosphere and oceans, but the effects did not stay in one neat box labeled climate. They moved through the whole house. Heat changed the air. The air changed rainfall. Rainfall changed plants. Plants changed animal diets. Ocean chemistry changed shell building. Shell building changed what lived and what got preserved. The whole system began answering back. And that is the near solution scientists have been circling. The ancient warming was not just a change in temperature. It was a change in connections. This is why the same event can look different depending on where you stand. In the deep sea, it looks like stress, extinction, and chemical pressure. In high-latitude forests, it can look like expansion, movement, and opportunity. In the bodies of mammals, it can look like shrinking, dispersal, or rapid adjustment. In sediment cores, it looks like a planet suddenly flooded with light carbon. These are not contradictions. They are different angles on the same machine. A warming planet does not produce one effect. It produces a cascade. And that cascade is the real story. The carbon pulse may have been the shove, but the Earth system was the thing that turned the shove into a global event. Models help scientists test this, not like crystal balls, but like controlled thought experiments with math and a suspicious amount of computing power. If you add enough carbon to the atmosphere, how much does the planet warm? If the oceans absorb that carbon, how does acidity change? How long does it take weathering on land to pull carbon back out? How quickly can deep ocean chemistry recover? The models do not replace the rocks. The rocks are still the witnesses. But the models help reconstruct the sequence of events, like detectives using the blood spatter, the footprints, and the broken window to figure out how the night unfolded. And the sequence matters. Because a short, sharp carbon pulse is different from a slow trickle. A warming that lasts thousands of years is different from one that lasts a few seasons. A recovery that takes more than 100,000 years is not really a recovery in any ordinary living sense. It is a geological recovery, which is to say, Very impressive and absolutely useless if you are a species that needed stable conditions right now. And that is where the story escalates again. The evidence suggests that after the carbon entered the system, Earth did eventually begin the long work of correcting itself. Chemical weathering on land can pull carbon dioxide from the air over time. Oceans can rebalance. Sediments can bury carbon. The planetary machinery has ways of healing. But those ways are slow. Painfully slow. Slower than forests can stay in the same place. Slower than some animals can adapt. Slower than food webs can remain recognizable. So yes, the planet moved toward stability again. But it did not simply rewind. This is the part that makes the clues feel less like a comforting ancient story and more like a warning with excellent documentation. The fossils do not say that warming equals instant doom. They say something more complicated. Warming changes the selection pressures. It alters which bodies work, which routes open, which habitats vanish, which organisms become vulnerable, and which lineages get a strange new chance. It does not just damage the living world. It edits it. And once that editing begins, the final draft may not look much like the original. So as the clues converge, the mystery comes into focus. The carbon signal, the warmed oceans, the stressed deep sea, the shifting forests, the smaller mammals, the open migration corridors, the long recovery, they all point in the same direction. This was a moment when Earth changed the rules faster than many parts of life could comfortably follow. But there is still one last question before the case can be closed, and it may be the most important one. When the fever finally broke, what kind of world was left behind? What was left behind was not a ruined planet. That would be too simple. The Earth did not become lifeless, silent, or permanently broken. Forests still grew. Rivers still ran. Mammals kept moving through the underbrush. Tiny organisms still drifted through the oceans, building their shells in water that had finally, slowly, started to become less hostile. From a cosmic distance, Earth would still have looked like Earth, blue, cloud-wrapped, alive. But up close, the living world had been edited. That is the answer the rocks keep giving us. The ancient fever did not erase life. It rearranged it. In the deep ocean, entire communities of small seafloor organisms were disrupted, and some never came back in the same way. In the water, chemistry had shifted enough to make the basic work of shell building more difficult. On land, forests moved with the climate. Animal ranges shifted. Some mammals appeared to have shrunk, as if their bodies were responding to heat, food stress, or a world where the old rules no longer fit. Other mammals found new paths through a warmer north and spread into places that had once been harder to reach. So the event was not just a disaster, and it was definitely not just a warm vacation for the planet. It was a filter. And filters are one of evolution's favorite, and least sentimental, tools. They do not ask what is impressive. They ask what works now. A body plan that thrived yesterday can become a burden. A tiny size, a flexible diet, a new route across a continent, or just being in the right place at the right time can become the difference between a lineage that continues and one that fades into the sediment. That is why this ancient warming matters. Not because it proves Earth can get hot and then cool again, though it can. Not because it gives us a perfect one-to-one copy of today, because it does not. The continents were arranged differently. The background climate was different. The species were different. The starting conditions were not ours. But the deeper pattern is hard to ignore. When carbon moves into the atmosphere and oceans fast enough, the Earth's system responds as a system. The air, the sea, the rocks, the plants, and the animals do not react separately. They pass the disturbance along. Heat becomes chemistry. Chemistry becomes ecological pressure. Ecological pressure becomes evolution. And once evolution has responded, the story cannot simply be rewound. This is the strange comfort, and the stranger warning of deep time. The planet has recovery mechanisms. Rain breaks down rock. Weathering pulls carbon from the air. Oceans rebalance. Sediments bury carbon away again. Earth is not fragile in the way a glass is fragile. It is more like an enormous, ancient machine that can absorb punishment and keep moving. But the gears turn slowly. So slowly that for the organisms caught inside the event, recovery may as well belong to another universe. A stable climate returning after tens of thousands or hundreds of thousands of years is good news for the rock record. It is less comforting if you are a small creature trying to find food next season. That is the scale mismatch at the heart of the story. Earth survives in deep time. Life survives by changing. Individuals survive, or do not, in the moment. And those three timelines do not care about one another equally. Today, when scientists drill into ancient seafloor, measure carbon in microscopic shells, or compare fossil teeth from warm forests, they are not just collecting old trivia. They are reading a warning written by organisms that had no idea they were leaving one. A tiny shell becomes a thermometer. A tooth becomes a climate report. A missing layer of carbonate becomes the outline of an ocean under stress. The past does not speak in human language, which is probably for the best, because it would have some very pointed notes. Instead, it speaks in fragments. Chemical shifts. Fossil turnovers. Bodies made smaller. Forests found where eyes should be. And when those fragments are placed together, they do not say, "Do not worry, this has happened before." They say, "Look carefully at what happened when it did." Because the most mind-bending part is that the descendants of that rearranged world are still around us. The mammals that moved through those warm forests belong to the broad story that eventually leads to many familiar groups, including primates, horses, and us, much later. We live in a world shaped by old filters, old crises, old openings, and old accidents. Our present is not separate from those ancient climate experiments. It is built on top of them. So the final image is not a dead Earth, or even a healed Earth. It is a changed Earth, a planet cooling slowly after a fever, while tiny shells settle through the water like ash from a fire no one saw, and small mammals move through warm forests beneath a sky that has already rewritten their future. And that leaves one question still hanging in the heat. If the rocks could remember that fever for 56 million years, what will they remember about ours?